think it's about time to start. So I'd like to welcome everybody back, or maybe also for the first time, to day 3 of the Topology and Strong Correlations workshop. Before we get started, I just wanted to say as a brief reminder, right, that we also have this Slack channel going on, and so I would very much like to again encourage participants to also go ahead and use this Slack for exchange with the speakers, discussions, questions, and so forth. Now that being said, it's of course my great pleasure to introduce our first speaker today. So today, as a first speaker, we have Naoki Yamamoto, who's a professor at Keio University. He'll be telling us about chiral soliton lattice and Qcd, and so we'll do it as in previous days. So for short questions, I think we can take them during the talk. If it gets longer or so, then I would say we defer it to the discussion after the talk, and so you have about 50 minutes or so, and I'll give you a warning towards the end. Okay, please, Naoki, take it ahead.
Okay, thank you very much. And first of all, I would like to thank the organizer for giving me this opportunity to talk here in this online workshop. Today, I'm going to tell you about this subject, chiral soliton lattice in Qcd. I slightly changed my title, but the contents are the same. And the chiral soliton lattice is a novel crystalline structure which carries topological charge in the ground state. And this kind of ground state is known to appear in condensed matter systems, such as magnets and liquid crystals. And in this talk, I will show you that the chiral soliton lattice also appears in the Qcd under extreme conditions. So our result will provide a new universality between Qcd and condensed matter physics. As I will show you, this chiral soliton lattice in Qcd also has the close connection to the chiral anomaly, chiral magnetic effect, and chiral vertical effect, on which Dima already gave a talk yesterday. So the talk today is mainly based on my recent works in collaboration with Thomas Brauner, Helena Koleshuba at the University of Stavanger in Norway, Shugan Fan at Fudan University in China, Kentaro Nishimura, and Akihiro Yamada at Keio University in Japan. So one of the main physics motivations in my talk is to understand the states of Qcd matter under extreme conditions. This is summarized in the Qcd phase diagram, typically as a function of baryon chemical potential and temperature. And there are several characteristic phases, such as hadron phase, where quarks are confined into hadrons. Quark-gluon plasma phase at high temperature, where quarks and gluons are liberated from hadrons due to thermal fluctuations. And also color superconducting phase at high density, which is a superconducting phase of quarks. However, nuclear matter or quark matter are often subject to the effects of a strong magnetic field or rotation. For example, the strong magnetic field or rotation of the order of Qcd scale may be realized in non-central heavy ion collision experiments. And also, a gigantic magnetic field may potentially be realized in compact stars such as magnetars. And so it would be important to understand the possible modification of the Qcd phase diagram in the presence of the magnetic field or global rotation. And in this talk, I will show you that above some critical magnetic field or above some critical intensity magnitude of the rotation, the ground state of Qcd becomes the so-called chiral soliton lattice. Okay. One can also ask, as a matter of principle, what happens to the Qcd vacuum when we apply a time-periodic circularly polarized laser with a sufficiently strong intensity and frequency. Although such an experiment is not feasible at this moment, And it turns out that even in that case, the Qcd vacuum is altered to be a novel Chiral lattice state, as I will show you later. So let me start with the definition of the Chiral lattice. The Chiral lattice has three characteristic properties corresponding to its name, chiral, soliton, and lattice. And the chiral stands for the property that it violates parity symmetry in the ground state. And next, soliton stands for the property that it has some finite topological charge. Finally, lattice means that the ground state spontaneously breaks the continuous translational symmetry down to some discrete symmetry. The ground state with all these three properties is called the chiral soliton lattice. Okay? And in fact, this chiral soliton lattice is known to appear in condensed matter systems, such as chiral magnets and liquid crystals. And chiral magnet is a class of magnets where parity symmetry is broken by the helical structure of spin. And here is a figure of chiral magnet. And this arrow shows the direction of the spin. And because of the helical structure of the spin, parity symmetry is broken because the direction of spin is fixed in only one direction. Also, because of the modulation of this spin structure, the continuous translational symmetry is also spontaneously broken. And so this is a lattice structure of spin. One can also show that each lattice carries some finite topological charge. Therefore, this spin structure is the chiral lattice. In fact, this kind of state was experimentally observed relatively recently in 2012. But from now on, I will argue that mathematically the same structure, the same ground state also appears in Qcd under certain conditions, such as finite baryon chemical potential in the magnetic field or global rotation or under polarized laser field. So let us start with low energy effective theory of Qcd. So let me first briefly review the basic properties of Qcd. In this talk, I will mostly consider two-flavor Qcd consisting of up and down quarks. The massless two-flavor Qcd has the SU2 left cross SU2 right chiral symmetry, which is spontaneously broken down to SU2 vector symmetry. And this is depicted in this figure. So this is a potential as a function of the order parameter of the chiral symmetry breaking, a sigma. And so this is this sigma corresponds to the radial direction, and this is a phase direction. Because of the finite expectation value of this sigma in the ground state, chiral symmetry is spontaneously broken. And consequently, we have associated number-Goldstone modes with this quantum number. Here, tau A is SU2 generator. And these number-Goldstone modes are nothing but Yukawa pions. And at low energy, we are interested in the dynamics of these Yukawa pions. And that is described by the low energy effective theory of Qcd called chiral perturbation theory. And the pion field living in this coset space for this chiral symmetry breaking pattern is parameterized by this representation. So sigma is a pion field. So pi A is a pion field, and tau A is SU2 generator again. And then we can systematically write down the most generic low energy effective theory of Qcd for pions in terms of this sigma in the expansion of derivatives and quark masses, and also external fields if there are any external fields. So this is why this is a model independent framework. So this approach, theoretical approach, is only based on the symmetry of the system. And at the leading order of the expansion, we can write down this kind of Lagrangian. So the first term is the kinetic term, and the second term is the mass term. Here, Fi is a so-called pion decay constant, which cannot be determined by the symmetry argument alone. So, for example, this can be fixed by experiment. And M pi is a pion mass. Okay. The essential ingredient in the low energy effective theory is the chiral anomaly. So let me also give you a brief introduction of the chiral anomaly. Let us consider the axial current with the third component of the isospin defined in this way. Classically, this current is conserved in massless Qcd. But due to the quantum effects described by this kind of triangle diagram, this axial current is no longer conserved. And the violation of this axial current conservation is proportional to E dot B. So this is the chiral anomaly. Now, the chiral anomaly has a very important property that this is independent of the energy scale, and this is exact at any energy scale. And in the case of Qcd, at low energy, the physical degrees of freedom are hadrons rather than quarks due to confinement. Then the fact that anomaly is exactly independently of the energy scale means that this chiral anomaly relation must be satisfied in the language of hadrons that couple to the axial current. So we have to satisfy this anomaly relation in terms of pion. So this is the idea of the anomaly matching. And from this condition, we can fix the coupling between charge neutral pion, pi naught, with two photons, E dot P. So this is a famous example of the chiral anomaly in Qcd. So this is the story of the chiral anomaly in the Qcd vacuum. But in medium, we have another type of the anomalous term, which is related to the chiral anomaly. At finite baryon chemical potential in the magnetic field, we have this kind of additional anomalous term. So mu B is the baryon chemical potential, and B is the external magnetic field, and pi 0 is charge neutral pion again. And the coefficient C is the same as the chiral anomaly coefficient given by 1/4 pi squared here. So this is the anomalous term that I reviewed in the previous slide. Okay. So let me give you how to understand this term. So let me give you a hand waving argument. For that purpose, let us first start with this anomalous term in the vacuum. Okay, pi 0 E dot B. In the static limit, this electric field can be written as a minus gradient of phi, where phi is the scalar potential. Okay. Now, by performing the integral by part, this can be reduced to this form. Now, chemical potential is a kind of a scalar potential. We may replace this scalar potential phi by chemical potential mu, and then we arrive at this term. Okay, so this is a very hand-waving argument. And originally, this anomalous term was derived more systematically based on the Bessel-Minowitten term in these papers. But we may understand this term in this way. And this term will be important in our following discussions. I will also give you another derivation based on the UV-IR matching of the chiral magnetic effect. The chiral magnetic effect is the effect that Dima gave a talk yesterday. So just to remind you of what the chiral magnetic effect is, chiral magnetic effect is a current along the direction of the magnetic field. of relativistic chiral fermions. For single chiral fermions, the current in the direction of the magnetic field is given by this expression, mu is the chemical potential of a single chiral fermion, and the signs plus and minus correspond to right or left-handed fermions, respectively. And this coefficient 1 over 4 pi squared is related to the coefficient of the chiral anomaly. Okay. The contribution of this chiral magnetic effect to a generic axial current with generic isospin index A is given by this formula in the case of Qcd. Here, Nc is the number of colors, mu B is the chemical potential associated with conserved charge, whose generator is proportional to tau B, and Bc is a generic magnetic field coupled to a charge whose generator is tau C. And DABC is the algebraic factor given by this expression, where tau A, tau B, tau C is assigned in each of the vertex of this triangle diagram. So this is just algebraic factor associated with generic generators, tau A, tau B, and tau C. Okay. And in the case of Qcd at finite baryon chemical potential in magnetic field, it turns out that the only non-vanishing contribution to the axial current arises only when the isospin component A is 3. And the result is given by this expression. Okay. Now, recall that this chiral magnetic effect is a topological current, and it does not receive any renormalization. This means that this chiral magnetic current must be reproduced at low energy in terms of the pion. This is very similar to the argument of the chiral anomaly, where chiral anomaly relation is reproduced in terms of the pion. Okay. Here, chiral magnetic effect must be reproduced in terms of pion. And in order to write down the anomalous term that is responsible for this chiral magnetic current, let us consider a local axial rotation, where quark is transformed in this way, and correspondingly, pion field is transformed in this way. Okay, here the factor 2 here originates from the fact that pion is made up of quark and anti-quark. That's why we have 2 here. Now, under this transformation, axial rotation, we have a variation of the Qcd action in this way. So the parameter theta 3 is the third component here, which is coupled to the third component of the axial current. And similarly, under this transformation, we have a variation of the action of the low energy effective theory in this way. Now, we require that the variations due to the chiral magnetic effect given by this expression match between Qcd at UV and low energy effective theory at IR. And this leads to the anomalous term at low energy, simply by substituting the expression of the axial current into this equation, we obtain the anomalous term in terms of pi, okay, in this form. Now, you can see that this exactly reproduces the Witten term that we have seen in the previous slide with the same coefficient. In this way, this anomalous term can be understood as the UV-IR matching of the chiral magnetic effect. Okay. Now, we understand that this term can be understood from this kind of matching. We can repeat the same argument for the chiral magnetic effect. So again, just to remind you, chiral vortical effect. The chiral vortical effect is a current along the direction of the vorticity or global rotation. And this is the expression of the chiral vortical effect for a single chiral fermion for right-handed or left-handed fermions. And mu is the chemical potential and T is the temperature. And the contribution of the chiral vertical current into the axial current with generic isospin index A is given by this formula. Again, NC is the number of colors, TABC is the algebraic factor defined in the previous slide. Mu B is the chemical potential associated with the conserved charge whose generator is tau B. Okay, and here we also have a new algebraic factor defined in this way. But it turns out that in the case of QCD at finite baryon chemical potential in rotation, all the components are vanishing in two-flavor QCD. But generically, so by repeating the same argument for the UV-IR matching, we get this kind of anomalous term again. And as I said, this new anomalous term is vanishing as long as we consider QCD at finite baryon chemical potential in a global rotation for two-flavor case. But more generically, in QCD matter, we have not only baryon chemical potential, but also isospin chemical potential. In this case, there is a non-vanishing contribution in this form, where we have not only baryon chemical potential mu B, but also isospin chemical potential mu I. I would also like to note you that in the case of three-flavor QCD, even without the isospin chemical potential, we have a non-vanishing contribution, not for pion, but for eta prime meson. But in any case, the message here is that we have anomalous term similar to QCD in a magnetic field. So the physics of QCD in a global rotation is very similar to the physics of QCD in the magnetic field in that sense. So that's why I will mostly focus on the case of QCD in the magnetic field, because we can simply repeat the similar argument for the case of QCD under rotation from now on. Okay. So summarizing what I have discussed so far and focusing on charge neutral pion sector, we can write down the low energy effective theory of QCD at finite baryon chemical potential in the magnetic field in this way. So the first term is the kinetic term of pion. The second term is the anomalous term related to the chiral anomaly. And the third term is the mass term for pion. Here, without loss of generality, I take the direction of the magnetic field in the z direction. And I assume that magnetic field is homogeneous. Now, one can ask, what is the ground state of this Hamiltonian? And this question was first addressed by Soeren and Stefanov, as far as I know. And Soeren and Stefanov conjectured that the ground state of this Hamiltonian is a parallel slack of pion domain worlds, although they did not give an explicit solution. And I want to give you an explicit solution. And in order to provide an explicit solution, it is interesting to notice that actually exactly the same form of the Hamiltonian is already known in the condensed matter physics. That is the Hamiltonian of chiral magnets, given by this expression. Here, J is the strength of the interaction between neighboring spins, and S is the magnitude of spin, and A is the lattice spacing. And phi is the spin angle as a function of the coordinate. Okay? And the first term of this Hamiltonian can be obtained by taking the continuum limit of the usual Heisenberg model for spins. And the second term is called the Gerusinsky-Moria interaction. So this is a lattice version of the Gerusinsky-Moria interaction, which is anti-symmetric with respect to the exchange of spin. Here, D is some vector which depends on the detail of the materials. By taking the continuum limit, one can show that this Gerusinsky-Moria interaction reduces to the to this form. This can be written in a way that this can be written in a way that the first derivative of the spin angle. Here, without loss of generality, I also took the direction of this D vector in the Z direction. That's why we have a derivative in the Z direction here. And the third term originates from the Zeeman term in the presence of the magnetic field in this form. So you can see that this Hamiltonian of chiral magnets takes exactly the same form of the low energy Hamiltonian of Qcd. The pion field. Rob, do you have any question?
Yeah, what's the physical origin of the Gerusinsky Moria term? Is there some
You mean this
anomaly?
term?
I'm not familiar with that term.
You mean this term? Gerusinsky-Moria interaction?
Yeah.
So this, microscopically, this originates from the spin-orbit coupling. So this is a relativistic quantum effect in materials.
Okay. Okay, but there's no anomaly.
There's generically no anomaly, yeah. But
Okay.
yeah, but they are similar in the sense that both originate from relativistic quantum effects. But
Yeah.
this is not
Okay.
necessarily anomaly. Yeah.
Okay. Thanks.
Okay, now you can see that these two Hamiltonians are mathematically equivalent. Pion field corresponds to the spin angle, and the first kinetic term corresponds to this term, and the anomalous term in Qcd corresponds to the Gerusinsky-Moria interaction. The mass term corresponds to the Zeeman term. But the ground state of chiral magnet is already known as the chiral lattice. Therefore, we can conclude that the ground state of Qcd is also chiral lattice under certain condition, as I will explain from now on. So again, so this is a figure of chiral lattice, and the chiral lattice is the one-dimensional lattice of topological soliton, which breaks parity and continuous translational symmetry. And I want to explain why the ground state of this Hamiltonian has these properties. For that purpose, let us first observe that this anomalous term or this Gerusinsky-Moria interaction are total derivative. Okay, they are just total derivative so that they do not contribute to the equation motion. If we write down the equation motion from these Hamiltonians, we obtain this kind of equation motion. The first term comes from the kinetic term, and the right-hand side originates from the mass term, okay? But you should be familiar with this equation motion because this also appears in classical mechanics. This is exactly the equation motion for a single pendulum. And we know that the equation motion for a single pendulum can be solved analytically by using elliptic function. And the solution is given here, where Sn is the so-called Jacobi Sn function. And Z bar is a dimensionless coordinate measured with respect to the pion mass. And K is the so-called elliptic modulus of the elliptic function. Oh, sorry, I missed your question. So maybe I got the question for the previous slide. Sorry. So how the field phi is related to the spin? So sorry. So maybe you ask the relationship between phi and S here, right? So let me give you a backup slide for that. So here. So this is a relationship between the spin variable S and the angle phi. So we are considering the spin as a function of z direction. So here we assume that the spins are frozen on this plane because the spin interaction on this plane is assumed to be much larger than spin interaction between this plane. And then the spins are frozen on this direction. And then the angle phi is defined in this way. That is the definition. And then by taking the continuum limit, this term reduces to this form. And also the Heisenberg Hamiltonian reduces to this form in the continuum. Does that answer your question?
Naoki, this is the coherent state basis, right?
Covariant basis. What is that?
This is the coherent state basis, you mean?
Covariant?
Coherent. Coherent, yeah. All spins in the same direction.
All spin. So this Sj and Sj plus 1 are not necessarily in the same direction. So this angle,
then it's
angle phi can be dependent on the coordinate. So this phi depends on the coordinate z. Okay. Okay, yes. Then let me proceed. So let's see. So here is a solution for the ground state, but in this talk, I don't want to explain you the details of mathematical analysis of this elliptic function, but rather I want to give you an intuitive understanding of the behavior expressed by this elliptic function. So for that purpose, let us consider two extreme situations. So here is a Hamiltonian again, and let us first consider the situation where the third term is negligible compared with the second term. Okay. In this case, we can complete the square in terms of del z pi, because we have del z pi squared and del z pi, so we can complete the square to obtain the minimum of this Hamiltonian, and the minimum is achieved when this del z pi is proportional to b with some prefactor. So in that case, pion field, the expectation value of the pion field grows linearly as a function of z. That is the first case. Let us then consider the situation where the second term is negligible compared with the third term. In this case, the first term is minimized when the pion field is constant, and the third term is minimized when the pion field takes integer multiple of 2 pi. Therefore, in this case, the expectation value of pi is given by the integer multiple of 2 pi. So these two are extreme situations, but generically we need to consider the competition between these two cases. Therefore, globally, the pion field wants to grow linearly as given by this, but locally pion field tends to stay at the integer multiple of 2 pi, which is exactly this form. And this form, this behavior is exactly expressed by the elliptic function. Now you can see that this expectation value of pion field spontaneously breaks parity symmetry. If a pseudoscalar pion has expectation value, then parity symmetry is broken. And also because of this modulation, continuous translational symmetry is also spontaneously broken. Okay. Now, I want to argue also that this ground state carries a finite topological charge, several types of topological charge. And actually, this system has several topological charges, such as baryon number, magnetization, and angular momentum. The baryon number density, NB, can be obtained by taking a derivative of Hamiltonian here with respect to the baryon chemical potential mu B in this way. So from this anomalous term, if you take a derivative with respect to this baryon chemical potential mu B, you get this, this term. And also, magnetization can be obtained by taking a derivative of Hamiltonian with respect to magnetic field. And from this anomalous term, you get this one. And in the case of QCD at finite baryon chemical potential and at isospin chemical potential, as I explained to you previously, we also have anomalous term related to the chiral vortical effect. In that case, by taking a derivative of Hamiltonian with respect to the global rotation, we get the angular momentum in this way. And as I will show you in next slide, they are related to the topological charges, okay? But for now, it is important to notice that all of these three quantities can be written as total derivatives, okay? They are all proportional to del Z charge neutral pion field. Now, let me explain why this baryon number is topological. And for that purpose, let us consider the baryon charge of each lattice. And the baryon charge of each lattice can be obtained by performing the integral of this baryon charge density over one period from minus half L to plus half L. Here, L is the period of the lattice. Now, as I said, this baryon number density is written as a total derivative. If we perform integration, then this gives the difference of the boundary values at plus half L and at minus half L. And we know these values, so they are just 2 pi and 0. And we also know the coefficient C is just the anomaly coefficient 1 over 4 pi squared, so that each lattice carries this baryon charge B over 2 pi. So we learned that each lattice per unit area carries this baryon charge, the magnitude of magnetic field divided by 2 pi. And similarly, we can obtain the expression of the magnetization and angular momentum in this way. And the important point here is that these values do not depend on the detailed profile function of the pion field. So they are just fixed by the boundary values. In this sense, these are topological charges. Okay. Now, I showed you that the ground state we are considering breaks parity symmetry, continuous translational symmetry, and also carries topological charge. Therefore, the ground state is the so-called chiral lattice. But we have not yet fixed one free parameter k called elliptic modulus. And in order to fix this elliptic modulus k, we have to minimize the Hamiltonian in terms of this parameter k. And from that procedure, we get this identity. Okay, here Ek is the complete elliptic integral of the second kind. So this condition provides us an optimal elliptic modulus k for a given baryon chemical potential and magnetic field. One can mathematically show that the left-hand side, this combination is bounded from below, and the minimum is unity. So this means that Chiral lattice is only realized when this magnetic field exceeds some critical value given by this expression. One can also show that when magnetic field exceeds this value, then the Chiral lattice has a lower energy compared with the QCD vacuum. Therefore, this is a necessary and sufficient condition for the realization of the Chiral lattice, as long as we can focus on the charge neutral pion within the applicability of this low energy effective theory. And similarly, we get the critical magnitude of the global rotation for the realization of the Chiral lattice at finite isospin chemical potential. Now notice that these critical values are proportional to the pion mass. And pion mass is finite in our real world because quarks have finite masses. But if we consider the world without quark masses, then pion mass would also be 0, in which case these critical values would also be 0. In such a situation, the QCD vacuum would be unstable against the formation of this Chiral lattice in an infinitesimally small magnetic field or infinitesimally big global rotation. But such a situation doesn't happen in our real world because of the finiteness of quark mass. So the stability of the QCD vacuum is ensured by the finiteness of the quark mass. Okay. From our analysis, we can draw the phase diagram as a function of the baryon chemical potential in the magnetic field. So as I said, above some critical magnetic field, the Chiral lattice phase is realized. Although I have focused on the charge neutral pion sector, we cannot generically ignore the effects of charged pions. And in fact, if we increase the magnitude of the magnetic field further, then one can show that charged pions become tachyonic. And this is the onset of the Bose-Einstein condensation of pions, although I will not go into details on this aspect. But in any case, there is a range of parameters where the ground state of QCD becomes the Chiral lattice.
We have about 10 minutes now. Okay.
Okay, thank you. So maybe, yeah, let me now change gear to another question of the QCD phase structure. So suppose that we have the QCD vacuum and we want to ask what happens to the QCD vacuum when we apply a time periodic circularly polarized laser with a sufficiently large intensity and frequency. Okay. Of course, this is not feasible within the current experimental reach, but this is a kind of matter of principle question. And it turns out in this case, again, the QCD vacuum becomes the Chiral lattice. And the theoretical technique to attack this kind of question of quantum many-body systems under the periodic laser field is the Floccus theory. And the Floccus theory is widely applied in the context of condensed matter physics to realize novel states of materials under the laser field. And this is also called Floccus engineering. So the idea of the Floccus theory is to map a time-dependent Hamiltonian under the time periodic laser field into the problem of the time-independent Hamiltonian. And let us first start with the Floccus theorem, and which is nothing but the temporal version of the Brookhaven theorem for crystals. The Brookhaven theorem states that the solution to the Schrödinger equation in a periodic potential takes the form of the periodic function multiplied by the plane wave solution. And similarly, Floccus theorem states that the quantum states of the time periodic Hamiltonian satisfying this relation takes the form of the temporally periodic function multiplied by some phase factor as a function of the time t. Okay. Now, because Hamiltonian and also this quantum state phi are periodic as a function of t, we can perform a discrete Fourier transformation in this way. And then by substituting this expression into the original Schrödinger equation, we get this eigenvalue equation, where on the left-hand side, the integer m is, the summation over integer m is taken for a given integer n. Okay. So from this procedure, we can map a time-dependent problem of the Hamiltonian into a time-independent Hamiltonian. But the price we have to pay is that we need to consider infinite number of states. And this is very similar to the idea of Karzai-Klein reduction, where compactified direction is decomposed into the infinite number of states. And then the resulting theory is independent of the extra dimension. And in this case, in our current case, the compactified temporal direction is decomposed into the infinite number of states, by which we can consider the time-independent Hamiltonian. And in order to proceed further, we need to make some kind of approximation. And if we are interested in the long time scale, much larger than the period of the laser field, then we can solve this theory perturbatively in terms of the expansion of 1 over omega, where omega is the frequency of the laser field. This is very similar to the usual technique of the perturbation theory in quantum mechanics. And we can obtain the Hamiltonian at given order. As the zeroth order, we get the effective Hamiltonian in this way. H0 is a zeroth component of this discrete Fourier transformation. And at first order, the effective Hamiltonian is given by the commutator of the Hn and H minus n, where Hn is the nth component of this discrete Fourier transformation. And so far, the discussion has been general, applied to any system, but we are interested in the application to Qcd. And for that purpose, let us consider a more concrete setup. So let us first specify the configuration of the laser field. So this is a gauge field as a function of the time and the coordinate z. Omega is the frequency and f is the magnitude of the electromagnetic field. We can easily confirm that from this gauge field, electromagnetic fields have the same magnitude f, and they are perpendicular to each other, and they are rotating right-handedly. So this gauge field corresponds to the Helmholtz plus 1 configuration. We can similarly consider the Helmholtz minus 1 configuration, but considering this situation would be sufficient for our purpose. Now, by substituting this expression into the case of two-flavor Qcd, we get the effective Floccus Hamiltonian. So we can explicitly compute this commutator to obtain this Hamiltonian, where Qf is electric charge for each flavor, plus 2/3 for upcock and minus 1/3 for downcock. And Jf5 is the actual current for each flavor. We can also write this flavor actual current by using the isospin triplet and isospin singlet actual current in this way. Okay. Now, at low energy, this actual current carried by pion is given by this expression. So by substituting this expression into this Hamiltonian, we get the low energy Floccus effective Hamiltonian. So summarizing what I have argued so far, so this is the low energy effective Hamiltonian. The first term and the third term as a time independent part of the original Hamiltonian, and the second term is the effective Floccus Hamiltonian induced by the laser field. Now the point is that the right-handed laser field induces the Hamiltonian proportional to the actual current, which is written in terms of the first derivative of pion. And then we should notice that this Hamiltonian has exactly the same form as the Hamiltonian that we have discussed for the Qcd matter in the magnetic field or chiral magnets, right? And then by repeating the same argument, the ground state of this Hamiltonian is again the chiral lattice above some critical magnitude of the laser field given by this expression. As a reference for the frequency comparable to 1 JeV, the critical magnitude of the laser field is 1 JeV squared. And certainly this is beyond the current experimental reach. But what we have found is that there is unknown parameter region of laser intensity where the Qcd vacuum becomes unstable against the formation of this novel chiral lattice. And we may call this Floccus vacuum engineering. Okay, so I think I used most of my time, so maybe let me go jump to the conclusion. So I have shown you that chiral lattice is a novel state of matter that appears universally, not only in condensed matter systems, but also in Qcd. And this chiral lattice has a close connection to the chiral anomaly, chiral magnetic effect, and the chiral vortical effect. And although I have focused on the case of 2-flavor Qcd, we can also generalize our argument to 3-flavor Qcd. And for example, in Qcd at finite baryon chemical potential under sufficiently large rotation, one can show that the ground state becomes the chiral lattice for the eta prime meson, not for baryon. And it would be interesting to consider possible experimental implications. And one immediate application is wire and Dirac symmeters in condensed matter systems where wire fermions or Dirac fermions appear emergently. When the interactions between quasi-particles lead to the chiral symmetry breaking due to the pairing, then we can repeat the similar argument for the non-Boston mode there. And in that case, for example, in the presence of the magnetic field or in the presence of the laser field, the ground state would be unstable against the formation of the chiral lattice. I think that's all. So thank you for your attention.
Yeah, thank you very much, Naoki, for this fascinating talk. I think we have quite a bit of time for questions still. So if you have a question, either just speak up or raise your hand, and I will call you or type it in the chat as you please. Rob.
Hi, could you go back to your slide where you had the form of the CSL, please?
CSL.
Or the equation for, before you
You
started
mean this
talking
one?
about it. There was a later one where you had the detailed form. Yeah, wait, yeah, okay. No, if you go back one,
What? That's one.
go back. Yeah, no, right. You went.
Slide 27 is what you mean, Rob, no?
I can't see the slide numbers.
You mean the solution? Which?
No, I just wanted to see the slide. Is it 20?
2 slides further.
Where you had the equation. Okay, in any case, you had a slide in which you argued that in the chiral limit, you were unstable.
Okay. That is here.
And yes, that slide. My question is, I'm somewhat surprised by that. If I'm in the chiral limit, there's no theta dependence.
No.
And
What dependence?
if I have massless quarks, the theory
Uh-huh.
does not depend upon the theta parameter.
Right.
So I'm somewhat surprised that you find an instability in the chiral limit. And that's my first question. I have a second question, but if you could answer that first.
So I still don't understand what you mean. So certainly in the massless limit, QCD is theta independent, but why is that related to?
I'm just surprised that there's an instability.
Yeah. So yeah. So
I mean, for example, your omega CSL, it diverges as mu I goes to 0. I'm also surprised that you find a rotation for non-zero isospin chemical potential. I don't understand that.
So for both, in the presence of both baryon chemical potential and isospin chemical potential, this critical magnitude is proportional to m pi. That's why if we take the chiral limit, this goes to 0.
Yeah, but okay, what happens if mu I goes to 0? Why is there something
We cannot
weird?
take mu I goes to 0 for the rotation case, because in that case, this anomalous term disappears.
Oh, I see, because it has to be bigger. But so why is there an instability for 0 pion mass? I just find that.
So instability is caused by this anomalous term, okay? So in the absence of this mass term, we have not only this kinetic term, but also this second term, which is proportional to the first derivative of pion field.
Yeah.
So it is energetically favored to have expectation value of this first derivative of pion field, right? Just complete the square.
Yeah,
And
sure,
then,
sure.
Yeah, that's the reason. Yeah.
Okay. Well, I just wanted to make a more general comment that may be related, and that is, I think what you're doing is certainly correct for small densities, but in general, the form of the Wess-Zumino-Witten term is not invariant at non-zero chemical potential and temperature. This was demonstrated by Michelle Titgat, Larry Truman, and I some time ago. For example, the comment that you have pi naught to 2 gammas is of course true in vacuum, but
I know that
in a
paper.
medium, you can have pi naught sigma goes to 2 gamma.
Yeah.
In a chirally symmetric phase. So things may be more complicated as you increase the density, and you have to include further anomalous terms.
Yeah, so here we are assuming some counting scheme. So we are treating mu b and b and also derivative as small expansion parameters, and we are considering leading order in expansion. That's why we ignore the higher order fraction.
Okay. Yeah.
So at least as a leading order, this picture would be okay. But as you said, if we consider higher corrections, then the picture may be modified. So
not higher expansion in the chiral field, just in density or temperature.
Yeah. Right.
Okay. Well, I don't want to. There may be other questions. Thanks. Nice talk.
Thank you.
Yeah, let's see if there are other questions. Please raise your hand or speak up. I don't see any right now, so let me ask a question actually. So to realize the effect, right? You need a finite magnetic field and you need finite baryon density, right? And so that's or rotation instead of the magnetic field, right? So that's not a regime that really the lattice can address, right? Because of the baryon density
So yeah, because of the same
right?
problem, yeah, at present we cannot perform a numerical simulation. But
that being that being said, now I mean, you also do your calculation somehow in infinite space, right? So do you know what would happen if you were to compactify the z direction? Would there still be a modulated phase, or is it then better to have a constant if you enforce periodic boundary conditions in z?
Well, I'm not sure if I understand your question.
Because your solution is kind of linearly growing in z. Right?
Yeah. In order to discuss the phase, I need to take the some dynamic limit, right? So that's why I'm not sure what do you mean by compactify the space. So in a finite volume, we don't have
right? Because
we don't have a non-vanishing order parameter.
Okay.
Yeah. But concerning your question on the possible realization of the lattice, my collaborator Tomasz Brauner and Helena Koreshiba and their collaborators also studied this Chiral lattice in QCD-like theories, like two color QCD and other type of QCD-like theory, which do not have a fermion sign problem, in which case one can, in principle, numerically test the realization of the Chiral lattice. Although this is not a real QCD. Yeah.
Yeah. Okay. All right. I don't see any other questions. So last chance. Okay, good. So then I would say let's thank Naoki again for this nice talk.
Yeah. Thank you very much.